Okay, so let's get back to solving some problems for that Calculus 2 review. So I see a question that popped up. I'm not sure if possible, but could you go over topics / vocab that we should look over, true or false section? Oh, okay. There won't be true or false sections coming up on this exam. It'll mostly be just the integration techniques and things like that. Yeah, so the wording on those, trying to illustrate what's going on, it's going to be a little bit different. So that component of the exam will be a little bit different. So we're going to be mostly focused on trying to integrate with techniques of integration, trying to apply those techniques of integration. So there won't be any, there'll be word problems, but you'll see something similar to that coming up. I have most of the material set up to kind of assist you in preparing. So hopefully that makes sense. I could try and touch on, though, if you want to see some of those, I'll pull that up in the meantime and try and get to that towards the end. Just give me a reminder once we finish up. So without further ado, let's get rocking and rolling. So we have x squared divided by the square root of 9 minus x squared. So where do we go from here? What is this thing going to look like? Well, we want to try and first take in this case, a trig substitution, because we have that square root. So we have x equals, well, where should we go with this? So we have the x squared appearing as a negative right there. So this should be x equals 3 sine of theta. Give me one brief second here. So in this case, if we have x equal to 3 sine of theta, notice that dx equals, in that case, 3 cosine of theta d theta. Okay? So from there, where do we go? Well, we can get our x values, we can plug in that, so we get 3 sine of theta, the quantity squared, divided by the square root of 9 minus 3 sine of theta, the quantity squared, and then dx is 3 cosine theta d theta. Okay? So with that in mind, where do we go from here? Well, we can end up getting, our numerator becomes 9 sine squared theta. Our denominator, oh, okay, so hold on one second. Okay, sorry about the technical issues. Hopefully we're back in action here. So where were we? We're on this problem, and then I saw some stuff about a question in regards to, what was it? It said, can we go over some topics / vocab? I'm not going to so much ask the vocab questions like you saw in past exams coming up, but if you do have questions towards the end, I'll be happy to cover that stuff, but you don't have to plan to take all those true-false questions. We're not going to be doing that this time around. We are going to focus more though on those integration techniques. You're going to be asked to solve integrals galore, along with applying those integration techniques. So the physics problem, center of mass, surface area, volumes, area between two curves, things of that nature. Just be prepared to see that stuff. So I want to make sure, and we'll touch on that towards the end, but in the meantime I want to make sure we're getting things rock and rolling with those integration techniques. So let's see if we can solve some problems, and once again, sorry for the technical issues there that I'm having. So in this case, we are going to be doing a trig substitution, and our trig substitution, since we have 9 minus x squared, we probably want to use, remember we take the square root of that one number, so that'll be 3, and then we want to use sine theta since it's minus the x squared. So 3 sine theta, and then dx would equal 3 cosine theta d theta. So when we take a look at this integral, we get 3 sine theta squared over the square root of 9 minus, well, once again we have a 3 sine theta, the quantity squared, and then the dx is 3 cosine theta d theta. So now just an FYI, this is 9 sine squared theta, so you could factor out a 9 and you get 1 minus sine squared theta. So keeping that in mind, we have 9 sine squared theta up top. You could write the bottom as square root of 9 times the square root of, well, 1 minus sine squared theta is just cosine squared theta. And then, oops, need a 3 cosine theta d theta. Okay, so in this case now, where do we go from here? Well, taking a look at this, we'd have the bottom becomes 3 cosine theta, and the reason why we can just make it the positive portion there is just because of where this cosine is going to be defined. So this is having us cancel here, and so we're left with an integral of 9 sine squared theta d theta. Well, that's convenient, because we recall that we have this integral, we can pull out the 9, and then we have a trig identity that we can use. It's going to be 1/2 1 minus cosine of 2 theta, and then a d theta. So now we have 9/2, and the antiderivative of 1 is just theta, and the antiderivative of cosine of 2 theta would be 1/2 sine of 2 theta. Now here's the tricky part though. This is where we need to know our trig identities, because in this case we can draw the triangle, right? You get sine of theta equals x divided by 3. So if we put our angle theta there, you have x on your opposite side and 3 right there, and then that means you have a square root of 9 minus x squared on the adjacent side. Now, keeping that in mind, that's theta, and it's not the 2 theta that we see down below. But there is a trig identity there as well that we could use. The sine of 2 theta equals 2 sine of theta cosine theta, and that'll be useful to us. So because now we can write this as 9/2, and we have theta minus 1/2 2 sine theta cosine theta. So the question is, will we be just solving integrals the whole time? No, we're going to actually do some applications here, and the same thing with the exam. You'll see like volumes, setting up volumes, things of that nature. Can you set up those equations? Can you write them 2 different ways using shell method, disk method? I won't ask you necessarily to, if I'm having you solve it, I don't care which method you use, but I want you to be comfortable using both ways, because there will be some where it'll be so much easier to do using say a shell method or using a disk method, and then also areas of cross sections. So you'll see all sorts of problems tonight that that are possibilities, things of that nature. So hopefully that'll help. It will be very similar to your WebWorks assignments. So that's, if you really want some ideas as to what might happen, check out your WebWork. That's the biggest proponent, and that's where a lot of this stuff is pulled from, is just different sort of WebWork problems or twists on those WebWork problems. So that's where I'm going to be pulling a lot of that stuff. So if you look at this now, we have this plus C, and hopefully that answers the question. If not, let me know. I'm happy to address it as well. So this is 9/2 theta plus sine of theta cosine theta. Oops, that's a theta plus C. So now we got to figure out what theta is too. Notice if sine of theta equals x over 3, that means theta equals the arc sine of x over 3. So we have this thing equals 9/2 the arc sine of x over 3 plus sine of theta. Well, what's sine of theta? We know that that's equal to x over 3 by looking at our triangle, and then times cosine theta, that should be the square root of 9 minus x squared, because it's adjacent over hypotenuse, all over 3. Okay, and we have that plus C. If you want to brush it up just a little bit, it's not necessary, but you can if you want. You get 9/2 the arc sine of x over 3, and then notice your 9's would cancel. You'll have plus 1/2 times x times the square root of 9 minus x squared, all plus some constant C. So hopefully that makes sense with the trig integrals, or trig integrals, I'm sorry. Trig substitution in this case, and we did along the way use a trig integral as the same song and dance here. So what is it called when you plug in a trig identity? In this case, I don't have a name for it. I'm just making a substitution is all. So like in this case, let's see, I'll put it in pink. We made this substitution going into this position right here. So that was just a nice little substitution. Actually, I did it over in this case. Just a nice little trig substitution, or not trig substitution in the sense of the integral type, but just a regular substitution where you're substituting that identity in there. So don't get confused. I know we're using trig substitution in a couple different ways. I want to make sure we're aware of just how to plug in those substitutions. Yeah, in terms of this though, you were using that substitution as well, right? Moving from here, from that step, that was also a substitution using a trig identity. So hopefully that makes sense. In terms of terminology, I'm not going to ask you, oh, here's what you have to call it or anything like that. I want to make sure you can work the problems and show your work along the way. That's going to help you earn points as well. So moving forward from here, when you see this one, what is our substitution in this case? Well, you get x equals, we're going to need 5 because of the 25, but now it becomes a secant theta. So 5 secant theta dx equals 5 secant theta tangent theta. Okay. So now, what do we do from here? Well, with this information, we can rewrite this integral. So we get 5 secant theta. It's a 5, and this is a secant theta. Tangent theta, and I forgot to put the d theta right there. So d theta. X squared, so we have 5 secant theta, the quantity squared, times the square root of 5 secant theta, the quantity squared, minus 25. And so you can rewrite this as 25 secant squared theta minus 25. You can factor out the 25. You get 25 secant squared theta minus 1. So that means that this integral becomes, oh, notice we have a 5 squared, so that'll be 25 secant squared theta right here. So one of your secant squareds and your secant theta will cancel. And your 5 will cancel off with a 25, and we'll have a 5 down below, so I'll pull that 1/5 out in front. You'll have a tangent theta up top. You'll have a secant theta down below. And then we'll have a square root of 25, and then we'll have the tangent, because secant squared theta minus 1 is just tangent squared theta, d theta. So now what does that mean? Well, that means we have this thing's 1/5 times the integral. We have tangent theta, d theta. We have a secant theta. We have a 5 tangent theta. Well, that's convenient because now our tangent thetas cancel, and we're left with this thing's equal to 1/25. The integral of 1 over secant theta. Well, remember, secant theta is 1 over cosine theta, so this whole thing is just cosine theta d theta. That's it. That's all there is to it. So our antiderivative, we just have this thing's 1/25 sine of theta. Plus some constant c. So now, if we have this up here, x equals 5 secant theta, notice we get x over 5 equals secant theta. So remember, that's going to be hypotenuse over adjacent. So if we have our theta sitting right here, hypotenuse is going to be x. Our adjacent side will be 5. So that means this is a square root of x squared minus 25 on that adjacent side. So now when we find the sine of theta, notice we get 1/25. Using that triangle, our opposite is square root of x squared minus 25. And our hypotenuse is x. And that is our final answer. So using another trig substitution, we can find it. So hopefully that makes sense. If not, let me know. I'll be happy to cover it again, or brush up anything that might be giving you difficulty. But hopefully that makes the trig substitution. I mean, we're seeing square roots over and over again. That should be the big thing coming up. And as long as we don't have a derivative of what's underneath the square root somewhere appearing in that integral, so then we're good to go. Yeah, so not scary. Yeah, they do seem, the more you practice them, the easier they get. The first time I remember I saw it, I was like, what the heck is going on here? It does get a lot better over time the more you practice this stuff. As long as you know the rules on when you plug in the secant theta, when you plug in the tangent theta, when you plug in the sine of theta, you're good to go. Yeah, the big thing, square roots, that's when you should be. Yeah, so they're still a little scary. That's fine. I will say, as soon as you kind of get the gist of, if you have square root of x squared plus a squared, for example, I know the substitution is going to be x equals a tangent theta, and you're going to have a trig integral somewhere along the way. If I have the square root of x squared minus a squared, I'm going to have x equals a secant theta as my substitution, and then the same thing for square root of x, or whoops, a squared minus x squared. You're going to have x equals a sine theta. And I'll actually tell you what this becomes in each case. It's actually, yeah, so it makes sense, but it's hard to repeat. I understand what's going to happen every time. There is no joke in terms of what's happening. Notice what you have is an a squared tan squared theta plus a squared. So you factor out an a squared and you have a tan squared theta plus 1. So this first one, what this reduces down to, it's just an a secant theta is what that piece becomes, right? And so, yeah, and I'd strongly suggest if you're struggling with which one to use where, just write it on a page of notes. It'll help tremendously. In this one, what you'll be left with, notice you get a squared minus a squared sine squared theta. So you get a squared and then 1 minus sine squared theta. So that becomes a squared cosine squared theta. So this will become, that whole thing becomes a cosine theta. And just as you saw on this one, notice we all of a sudden popped out with 5 tangent theta. So essentially the a, what you'll be left with when you plug in x equals a secant theta, you'll get an a tangent theta. Now, you are going to have that dx always involved. So that makes it a little bit trickier, but at the end of the day, the square root business will go away, and that's why we use those substitutions every single time. It's the same song and dance. There's no tricks to that. Those are chosen for a reason. Now, you could have gotten away with, in the one case where we used x equals a sine theta, we could have had it be a cosine theta being our substitution. You can still work out a solution that way. It's going to be a little bit trickier with your dx's and how these things are defined. So that's the trick